Well, hello, we're back in the underground basement lab again. We have the same antenna as we had before. It's the Harvard Engineering antenna, the little circuit board antenna, the quarter wave monopole, which is part of the Harvard Engineering leaf nut lamppost control system thing. And the last video we had this sort of vaguely similar setup, but what we were doing is turning the antenna around on this axis around here through 360 degrees. We moved it every 45 degrees, and the idea of that was to find out whether or not it is directional. So do we get a better received signal in one direction than another direction? And Mark Steele actually commented on the video and said, why didn't you use a turntable? I thought that's actually a really good idea. So this is a Mark Steele inspired video. So I've made a Lego Mindstorms turntable. I've raided my kids' Lego, took apart their Rubik's Cube solver. So we have a Lego motor here and the Mindstorms controller, which is hooked up to a Linux PC, running a Mindstorms bit of software I wrote to move the motor around. And we have the software-defined radio attached as well, of course, which is going to take our measurements for us. So what will happen is when I start this program off, you'll get two figures on the screen. The figure to the left-hand side will be the azimuth direction that the antenna is facing in. So we're starting here from 0. It'll turn around in a clockwise direction. Through 360 degrees, every 2 degrees, it will take a measurement. The second figure you see will be the received signal strength at that position. So I'll set this off now and I'll go and have a cup of tea and leave it to it. I don't want to be in the room while it's running this, because what will happen is potentially my body being here moving around will disturb some measurements and you won't get an accurate reading, and we want it to be as accurate as possible. The location here is it's my basement where I live, my home, and it is completely underground. We're surrounded on 4 sides here by solid ground, probably London gravel or something like that, I'd expect. And the ceiling is actually covered in plasterboard, but it's plasterboard and it has one of those sort of foil backs for a bit of insulation. So this is, it's not quite a Faraday cage, but it's fairly RF proof. I don't get a very good mobile phone signal here, it's quite low. I can't make phone calls here. I had to use Wi-Fi calling. But apart from that, it's a fairly quiet RF environment, so we shouldn't get much outside interference. The transmitter I'm using is it's a Cantenna I made for the last video. It's up there, you see, and it's transmitting from a software-defined radio, and we're receiving down here, and this is where we'll take our measurements. So I will set this off and I'll leave it to it. You'll be able to watch it. I'll fast forward the video and I'll be back after a cup of tea. Right, so the test is completed now. We've gone through 360 degrees at 2 degree intervals with this test setup here. And what I'll do now is I will send that file to another laptop I have with Excel on, and I will plot a graph with Excel of the results of this test, and we'll see whether or not this antenna is in fact directional. So here we are. We have a antenna pan on this spreadsheet here. All I've done is I've put all of the results down in the columns here. So that's all the received signal strengths. And you plot that onto this thing here. It's called a radar chart, like this. And what you can see is this up here is pointing there is north at 0 degrees when we had it on the turntable. And then the antenna turned around 2 degrees each time, and each time it turned around we took one measurement. And what we can see is that it's not completely circular, you wouldn't expect it to be, but it's roughly a circle. So the gain around 360 degrees around the antenna is roughly equal. I'd say that it's probably 1.5 dBs difference in there. And we thought about why that could be previously. It is basically because of the shape of the circuit board. There is more ground plane here, and so you tend to have slightly higher gain here, just because of the physics of how the antenna works. So there we are. That is a measured antenna pattern for that Harvard Electronics antenna from this thing here. And we see that it is an omnidirectional antenna. It transmits and receives pretty much equally in all directions, around 360 degrees. So then we put on this little reflector on our antenna here. You see the reflector here. And let's see now what that antenna pattern looks like. What we'd expect is, as I said before, it would be somewhat squished, elongated, so it'll be squished down there, and we'd have more signal over here and a bit at the back as well, but the side should be quite a lot lower because the whole thing's squished, and that is what gain is. Gain is where you have the higher signal strength in the direction of forward gain of that antenna. So basically where the antenna points, where your TV aerial points, is the direction of highest gain. So let's start the test now. Okay, that's it. It's complete. We've now done a full 360 degrees sweep with this antenna here. And what I'll do now is I'll get that results file as before. In fact, you can see that as well, why not? Here we are. So that's the end of that test there, you can see. There's a file here called map. If I look at that file there, you can see all the readings we have. And you can see actually right away, can't you, that when it's pointed directly at the transmitter, we get neg 21.81. When it's pointed away, we get neg 28. So already we see there is about, what is it, 7 or so, 6.2 dB difference between those two readings there, which is really good. That shows that our reflector is working. We have now got a directional antenna. So I will upload this, and we will plot that on another graph and see what it actually looks like. Let's have a look at our little reflector. Bearing in mind it's made out of a bit of cardboard and Lego and silver foil. It shouldn't be too good, should it? The best signal we have here is minus 26, minus 27 maybe around here, dBs on our receiver. And this is the pattern for the reflector antenna. And as you can see, that's the middle here, that's where the antenna is. We have this squished pattern here. It's a bit skew with because it's tin foil and a bit of cardboard, and so it's going to be a bit of a mess. But you see the idea. A higher gain antenna has a better signal strength in the direction it points. The back lobe here, that's the rear lobe. That's a fairly common thing to have. And also, potentially when we point the antenna towards the wall, when it's pointing the other way, so towards here is where the back wall is, we'll be receiving some reflections where the signal bounces from the transmitter off the wall into the antenna. So that explains the lobe here. But the forward lobe, the lobe of maximum, the signal here is neg 19.77, and the best signal we had here, about here, is negative 24.88. So basically we've got about 5 decibels gain, 5 dBs gain, just by putting this reflector on the back of the antenna round here. It's also really handy because if you want to pick up this signal here, if you're maybe receiving TV or radio, it could well be that you want to receive the transmitter here or base station here, and there could be another base station or transmitter here that you don't want to receive. And what we've done here is we see that the one here would be quite a good signal because that's where our gain is, but here we have a null. So even the base station or transmitter is here, it might be quite powerful. You're going to receive a much, much lower signal because that isn't in the pattern of the antenna. Let's compare the two side by side now. And there we are. And we can see that this is the directional antenna here. The orange is the directional antenna. The blue is the omnidirectional antenna. And that is the difference between a directional antenna and an omnidirectional antenna. Something which I think some people maybe do not understand. You can get high gain omnidirectional antennas. But what there'd be is something a bit like this here. So the antenna I have here is a 3.5 gigahertz. It's not really high gain. It's a few dB more than this antenna here. It's not as high gain as this one here even that we made. But what we have here is we have stacked Hertzian dipoles. So we have one here, that's the top of it there. That's at the bottom there, the ground. And we have another one here, that's the top, and that's the ground. And we have another one here, the top and the ground. So they're 3 Hertzian dipoles. They're not quite the length they should be for this antenna. And what we've done to compensate is they've put a coil here. So that's the antenna track there on the PCB, just going backwards and forwards, zigzagging. So it makes it electrically the right length, but physically it's a bit smaller. It's not quite as efficient as a full-size antenna, but it makes it a bit smaller. This one actually is a 3.5 gigahertz. And this came from a 5G test space station that I have here. That runs at 3.5 gigahertz. So there we are. That is a moderate gain 5G antenna. A proper high gain antenna is completely different. I mean, our one here is it's got a bit of gain. What is it? So let's have a look at the values here again. Maybe sort of 1, 2, 3, 4, so 6 dB gain. So with 2 dB gain of the vertical antenna, it's about 8 dB gain over that isotropic antenna which radiates all around that sphere. This antenna here, this is a high gain antenna. This is a 5.8 gigahertz high gain antenna. It's a patch antenna. It's always patches here, all run in phase. And they'll all transmit, and you'll get a signal pattern a bit like the one we see here, but it'll be a lot smoother because it's obviously made properly rather than a bit of foil. And it'll be a lot thinner here and a lot longer out here, and you'll see less of a big lobe at the back. But this here is actually a high gain antenna from a 5.8 gigahertz base station, which I've currently got in use, but I took it down just so we can see this antenna here. That's the high gain antenna. The gain of this, I believe it might actually be labelled on here. No, it's not labelled on here. I'd guess this could be sort of 16, maybe up to sort of 18 dBi gain for this patch antenna here. So proper high gain antenna. The antenna we have here, our little bodge antenna here, it's not really high gain. But as you can see from the comparison here, it's very, very obvious that the antenna on its own, just this antenna here, the basic vertical antenna here, is omnidirectional. And we can see that proven here with an antenna test. And compared to a reflector which completely changes the antenna pattern and makes it not omnidirectional. So there we are, that's our antenna comparison.